Hi guys, I am Dr. Nandapalaji. Today we are discuss about the topic of effect of magnetic field and isotope effect of superconductors. Like as superconductors are materials that can conduct electrically without resistance. But what happens when you add a magnetic field or change the atoms inside them? Today we explore two fascinating aspects: magnetic field effects and the isotope effect in superconductors. Introduction of this topic. This presentation delves into the intricate effects that magnetic fields and isotope variations have on superconductors, highlighting key concepts and phenomena like as an a magnetic field effect. Influences of superconducting parameters like as superconductors loss all resistance below a certain critical temperature Tc, but they also have a critical magnetic field beyond that superconductivity vanishes. Like as magnetic field significantly influences various superconducting parameters such as transition temperature, critical current, and the overall stability of the superconducting state. Understanding how magnetic field alter these parameters is crucial for enhancing superconductor applications, performance, and reliability. And then the effect of this lead to the Meissner effect, where magnetic fields are expelled from the superconductors. Critical magnetic field. Because the critical magnetic field represents the threshold at which superconductivity is destroyed. This slide will explore the theoretical frameworks and the empirical observations on how different materials exhibit varying critical field strength and the implications for their practical use in superconducting technologies. In like as the superconductors and the isotope effects of superconductivity. In superconductivity, have two different types of materials: one type 1 and type 2 superconductors. In type 1 superconductors, expert all magnetic field until the critical field is reached, then they become normal. And type 2 superconductors allow particle penetration of the magnetic field in vortices and can stay superconducting under strong field. This is makes type 1 material like niobium, titanium super useful and high field applications like MRI machines or particle accelerations. And the isotope effects of role in superconductivity theory. Now, what about the isotope effect? Isotope are atoms of the same element but with different masses and strongly enough changing the mass of atom in a superconductors can change the critical temperature. The isotope effect is crucial understanding superconductivity as it demonstrates how changes in atomic masses affect the superconducting transition temperature. Theoretical framework suggests uh, that heavier isotopes lead to lower critical temperature value due to the reduced phenomena frequency and the weaker electron phonon coupling. This phenomenon supports the electron phonon interaction theory as a mechanism for superconductivity. In 1950, experiments showed that when lighter isotopes were used, the critical temperature increased. This was key evidence for the BCS theory of superconductivity. In temperature depends in different isotopes of the same element exhibits varying critical temperature, which highlights the significance of isotope effect. For example, in superconductors like lead, studies have shown that this transition temperature decreases as heavier isotopes are used, showcasing the direct correlation between mass and superconducting properties. This relationship has practical implications for material selection in superconductor development. experimental of finding on isotope substances. Numerous experimental studies have validated the isotope effect, particularly in elemental superconductors and their compounds. Research demonstrates that subsisting isotopes lead to measurable change in critical temperatures and other superconducting properties. Confirming theoretical predictions, these experimental findings are instrumental in advancing the understanding of superconductivity and guiding the development of new superconducting materials. In conclusion, BCS theory says the superconductivity arises when electrons from pairs via variation in the atomic lattice called phonons. Heavier isotopes vibrate slower, weakening the electron pairing and thus lower temperatures. So magnetic field can suppress superconductivity but also enable powerful technologies, and changing atomic masses reveals the deep quantum nature of superconductors work. Superconductors are not just science fiction, they are the future of energy, medicines and transportation, and it all hinges on the sub subtitle dance between the magnetism, temperature, and atomic mass. In summary, both magnetic field and isotopes effects play a significant role in the behavior and performance of superconductors. Understanding magnetic flux spinning mechanisms in vital for maintaining superconducting states under external influences, while the isotope effects provides critical insights into the fundamental theories of superconductivity, revealing how atomic mass influences superconducting properties. Thank you. Thank you, guys.